Variation-aware modeling method for MRAM behavior model using the System-Verilog. The abstract. IP verification is an essential process while designing IP. It's become more efficient and significant with the increased demand for silicon in automobiles. IP verification includes verifying the logical operations, which runs logical operations and requires behavior models written in Verilog or VHDL. Behavior models are essential for small size gated to large memories. For small size circuits such as gate or standard cell, it's easy to implement all operations. However, large sizes IPs such as memory usually reflect only key operations because it is impossible to implement all the detailed operations and consider physical characteristics. In addition, in conventional modeling methods, some specialized devices such as MTJ devices for MRAM that having unique random characteristics cannot be supported. In this paper, we introduce memory-based cell modeling method, which enables various test operations for embedded MRAM. The proposed modeling method are implemented for solid IPR validation and it supports not only MRAM but also various types of memories. Introduction. In general, behavioral models are not more complex than circuits or physical layouts because they reflect only the logical operations of IP. For example, in the case of SRAM, the speed series which data is recorded is simply presented as a register in high definition language HDL description language. It's similar to the demand for an IP validation, and demand for the behavior model has also increased. Normally, various verification methods are being studied to increase the integrity of the behavior model. However, from the IP validation perspective, it is as important to enhance the behavior model itself as to verify the behavior model, because the model that are modeled in the detail support IP verification scenarios but for verification. In this paper, we introduce the memory bit cell modeling method for an MRAM behavior modeling using System-Verilog. Our modeling method supports solid verification and reflects the right time variance and right voltage variance. This figure 1, bit cell array variation aware simulation illustration. Section 2, related work. Behavior models are essential for system-level logical simulation. The behavior model simplifies the complex behavior of the individual IPs and enables logic simulation. So for simple circuits such as standard cell, modeling is easier in the most of cases. However, for big circuits such as memory, it is almost impossible to implement all analog circuit-based operation into behavior model. Therefore, most memory behavior model only implemented the important main functions such as read, write, scan, shift, and capture. As the importance of the chip verification increases, the need to implement the test functions also increases. Many studies, including us, have tried to model the complex test functions. Some of them use Verilog A to model the programmable metallization of cell PMC, which is a non-volatile memory device that generates oxide through ion flow and uses this behavior model to adjust the electrical resistance value to store data in the cell, as similar with the MRAM MTJ. And this prior works modeled for the operation of the PMC cell using the Verilog A based on the previously measured IV characteristics of the PMC cell. However, Verilog A modeling is more complicated and time-consuming than digital modeling such as Verilog or System-Verilog. Considering the regions for the existence of the behavior models, it is clear that a modeling with Verilog or System-Verilog is most desirable. In addition, other previous studies have modeled along operations such as PLL with high accuracy and System-Verilog alone. PLL circuit is used for clock generation and clock and data recovery and high-speed IOs. In this case, the analog operation of the PLL, such as PLL rocking behavior, jitter, and phase noise, were models using System-Verilog that are used for pre-silicon digital verification. Because the System-Verilog modeling methodology provided more data types and higher abstraction than Verilog A, more accurate and flexible models could be implemented. Specifically, Verilog A is a language used for analog simulation. With the PLL characteristics that requires consideration as both digital and analog operations, it is advantageous to use System-Verilog rather than a Verilog A. Section 3. MRAM behavior and modeling. Most memory operations can be simply implemented with a behavior model. This is because, from an operational point of view, writing and reading in a memory is a simple operation of storing and reading data, and in the case of the SRAM, in which bit cell is implemented as a set of transistors, this is expressed as a register in behavior modeling. However, MRAM, an emerging memory of non-volatile memory, has a unique random characteristics of the magnetic tunnel junction (MTJ) bit cell device. To run internal test operation for MTJ devices, conventional modeling method could not support. The following sections introduce the modeling method of MRAM behavior model. MTJ background. MTJ has a structure with two magnetic layers separated by an insulating barrier layer. The tunneling current flowing through the MTJ is determined by the thickness of the tunneling barrier and the voltage supplied to both ends. The determined tunneling current may change the magnetization direction of the magnetic material at both ends. In addition, the magnetoresistance of the MTJ changes according to the combination of magnetic layer directions. So MTJs with these characteristics are main devices used in MRAM, which are illustrated in Figure 2. However, variability and endurance issues occur in the higher voltages. So accordingly, the MRAM trimmed the right voltage to find and use the optimal write-off voltage according to the process changes. Figure 2. Data record methodology of MTJ device. DB. MRAM write operation. 4. On existing memory write operation, write 0 or write 1 is only a single operation because a single write operation can ensure data writing. However, due to the probabilistic writing characteristics of the MRAM MTJ device, a single write operation cannot ensure the write. To overcome these probabilistic write characteristics, the MRAM of the Samsung Foundry has multiple internal write and read operations in a single write operation. This internal write operation has probabilities, so that using the multiple internal write operations, the memory achieves an almost 100% write probability, and the internal read operation ensures a write operation. In addition, using a write verify scheme with write flag, MRAM notified the write completion status. However, due to this multiple probabilistic internal write operation, write time rather than a conventional SRAM is variable. In addition to time variation, MRAM has a write voltage variation also. Since MRAM is a resistive memory, the MTJ write voltage characteristics also has a variation following the process variation. The figure 3 to 4 illustrates our MRAM write operation. Just see modeling method. And in memory bit cell modeling method, we use two different modeling approach. time variance and voltage variation, and as the probabilistic write operation of MTJP cell in MRAM, the write time might vary for each write cycle. That is, the write voltage characteristics also has variation according to the process variation. Following the section describes each modeling method using various sample Verilog code. Figure 4. Write operation timing diagram of MRAM. Figure 5 is abstract timing variation modeling. Figure 6 is conventional memory register. Is 1. Time variation modeling. In this modeling method, a random write mode is added to the MRAM behavior modeling using a random internal write operation with the actual write operation of the circuit. Using the urandom range System-Verilog system task, individual internal write operations allows users to define the write probabilities. Based on the probabilities, each internal write sequence could continue to or stop internal write sequence in illustrated in Figure 5. This random function generates all possible write variation and keep proceed the internal write operation to achieve proper write operation. However, writing operation behavior models must eventually be ensured. Thus, when the write time reaches the limit of the specified write time, the write operation occurs. So from this mechanism, the write time fluctuations and ensures proper write operation with the specification. 2. Voltage variation modeling. In this modeling method, the change in write voltage is caused by the process variation. Because of this variation data is occurred during fabrication, appropriate variation characteristics must be obtained from the process designers to model the voltage variation. Table 1 describes the fair bit calculation based on voltage variation data provided from the process engineer. From the silicon-based write voltage characteristic, we can model the write voltage recognition operation using the System-Verilog language. We generate individual minimum required write voltage for all bit cells of the MRAM and use that voltage information while the writing data for bit cells. Since the write voltage characteristics of the MTJB cell follows a normal distribution, we use $normal System-Verilog task to generate the minimum required voltage for the bit cell. In addition, to store the individual minimum required voltage for each bit cell, a type-defined syntax is used to create a user-defined data type called mbit. Figure 6 is illustrate the conversation, the memory defined, and Figure 7 illustrate our proposed memory defined, which can contain the reference voltage value. So, and the Figure 8 is megabit MRAM write reference voltage profile. The 4 simulation result. The main purpose of this model is to use variant-aware test operation while verifying the digital non-volatile memory assist DNA IP operation for embedded MRAM. Figure 9 illustrates a conventional fixed write time simulation with the signal diagram with a Verilog simulator. As the write time is fixed, write busy flag WBF, a signal rise and fall in a regular while sequential writing, as illustrated in Figure 10 times variance operation. Verilog model allows write time variation in random time mode. In addition, using the voltage variation mode, unintended write failure operation for a bit cell does not satisfy the required minimum write voltage may be built. It can also be seen in the write failure which increase or decrease in terms of test pins setting by the change the reference write voltage using the test pin. Figure 8 and Table 1 represent a fair bit number and the ratio of embedded MRAM in terms of writing voltage trimming. Originally, this variation data was provided as voltage values from the process engineer. However, due to the security issue, it has been replaced with a streaming value for the model, not an actual value. The variation-aware model operation is verified with the DNA IP, which controls the MRAM for IP validation. Furthermore, this voltage-aware write operation also cross-checked with the Siemens TM-based solution under development to support MRAM in the future. Table 1. Train value with the failure bit cell count to write 0 case and write 1 case. The figure 10 is a fixed time write operation simulation result. Figure 9 time variation write simulation result. Conclusion. IP verification is essential to achieve the reliability of the Foundry library from the perspective of the Foundry business. In addition, the importance of each such verification is higher for basic IPs, such as embedded memory, while it is almost impossible to implement all actions for behavior modeling as many operations as possible is good for robust IP verification. To improve the reliability of the underlying IP of Samsung Foundry, we implement variation-aware testing method using the System-Verilog language in the behavior model. The behavior model we developed supports supports variation-aware operation while testing and preventing avoidable human errors. In addition, the modeling method we propose can be extended to various types of IPs written in the System-Verilog language. Furthermore, our proposal utilizes not only circuit characteristics modeling, but also real process data values of MRAM bit cell characteristics, and applied them to the behavior model. Through this, various test functions, timing, trimming, and calibration characteristics required for verifying MRAM, a complex memory, were implemented, making it possible to perform more precise pre-silicon digital verification than before. I'm sorry. Okay, required. The acknowledgement. We'd like to express our deepest gratitude. Okay. Look, today I read this paper. Variation-aware modeling method for MRAM behavior model using System-Verilog. Thank you for your time and see you next time.